Hi, so today we are going to learn Lorentz force acting on a moving charge which is moving in a magnetic field. We know from before that force acting on a static charge is given by Coulomb's law, and that force is equal to Q into E. And this force is of electric nature. But when the same charge moves in any magnetic field, let's say B with velocity V, here it can be shown with the help of a diagram. Here you have a magnetic field B, and at some angle a charge Q is moving with velocity V. Let the angle is theta. Then a new force, along with electric force, a new force, force magnetic, starts acting on this moving charge. And it is given by H.A. Lorentz. As per Lorentz law, H.A. Lorentz law, the force net on this moving charge Q will be given by this formula. It will be sum of the two forces, force electric and force magnetic. Force electric and force magnetic. This is the net force acting. This is your Lorentz force. And you can write it in extended form. Force electric is equal to QE plus force magnetic is equal to QV cross B. So magnetic force actually is equal to your QV cross B, and this is your net force given by Lorentz law. Net force on a charge moving with velocity V in any magnetic field B at an angle theta. So this is the net force. So what is the direction of this magnetic force? This force magnetic will be perpendicular to both V, and also it will be perpendicular to B. It will be perpendicular to both. You can see in diagram. Suppose you have a plane which is containing V in this very direction, and take B in some other direction, and it is making some angle theta. So you will assume a screw at this very place. A screw can be assumed. When you assume a screw, I am assuming one screw at this very place, and move from first vector to second vector. Here you have force magnetic, which is equal to QV cross B. This magnetic force is actually a product of vector product of two vectors v and b. So you will be moving from first vector to second vector. So when you wind this screw from first vector to second vector, you will find that screw is unwinding and it is moving in anti-clockwise direction, so it is coming out. And it will come out in a direction perpendicular to this plane. In this direction, the screw will come out. And this is the direction in which the force magnetic is acting, because it is vector product of the two vectors. So this direction can be shown, can be given the direction of force magnetic. If you, in second case, the same plane I am taking and the two vectors have different directions. Here now B vector is in downward direction and V vector in upward direction, which is at an angle theta. Then for finding direction of magnetic force, this force, Lorentz force, I'll place one screw at the meeting point of the two vectors. Here I am placing a screw and I move the screw, wind the screw from first vector V to second vector B. I find that screw is winding in clockwise direction. So screw is actually inserting inside, tightening inside. So now the direction of force magnetic will be along inward perpendicular direction. In this case, direction of force is this one. And you will find that whatever be the value of theta, if you increase the theta, in that case also force will have the same direction. Force will be perpendicular to both V and B, and it will be perpendicular to the plane containing V and B. So this was about direction of magnetic force. Now using this definition we can define magnetic field also, unit of magnetic field. We can define what is one unit of magnetic field. So if we take force is equal to 1 Newton, let me convert this into angle form. This force magnetic becomes equal to QVB sine theta, magnitude of force. So I am taking magnitude of force. If it is 1 Newton, charge is equal to 1 coulomb, velocity is equal to 1 meter per second, and sine theta also is equal to 1, means theta is equal to either theta is equal to 90 degree. Okay, theta is equal to 90 degree. Then by the formula, let me name this one, formula 1, equation 1, B is equal to force divided by QV sine theta, and therefore B is equal to 1 Newton per 1 coulomb into 1 meter per second. Second goes in numerator, per second, and sine 90 degree is equal to 1. So everything comes 1. So it is equal to 1 Newton second per coulomb meter. So this is unit of your magnetic field. I have written in extended form so that it may not be considered as centimeter. Okay. Therefore, SI unit of magnetic field B is equal to this much, and this is called 1 Tesla. Tesla is a very large unit. Considering the magnetic field given by our Earth, the magnetic field provided by our Earth is of order of 10 to power minus 5 Tesla. So from here we can consider that Tesla is a very big unit, because in terms of Tesla, Earth's magnetic field has value, has order only 10 to power minus 5. So a practical unit of magnetic field is used, and that is your Gauss. 1 Tesla is equal to 10 power 4 Gauss, and this is very practical unit. Generally we have magnetic field anywhere present can be very easily written in terms of Gauss. Now magnetic field due to a current carrying conductor, and force. Okay, force on a current carrying conductor placed in an external magnetic field. Suppose you have a current carrying rod of length L. It is having cross-sectional area A, and it is placed in an external field. Here you have external field of magnitude B. Now A is cross-section area, L is equal to length of conductor, B is equal to magnetic field, we are assuming all these quantities, and N is equal to charge density, means number of charges per unit volume. So if number of charges is capital N, let number of total charges is equal to capital N. Then N is equal to capital N charge density, number of charges per unit volume. So divided by, for volume, area into length. So this is your total number of charges. Total number of charges is equal to NaL. This is number of charge, number of electrons. So therefore the total charge in the conducting rod total charge Q can be written as number of charge into charge on one electron, that is E. So this is your total charge and this is equal to NaLe. Now we will apply Lorentz force in this situation. We know that F magnetic is equal to Q V cross P. It is a vector product of two vectors. The force is vector product of two vectors. When I replace charge with this value NaLe V cross B. So here we find that this can be replaced by charge density also, current density also. What is current? This is your total charge and this can be replaced by your I into A. Means you know that current is equal to charge per unit time. So in place of charge you can write I into T, I into T into V into B. Now, and we know that how current and direct velocity are related to each other. We know that I is equal to NaE V direct. And if you convert this I into current density, then it is turned into a vector. I is not a vector, I is a scalar. But current per unit area, I per unit area, this is a vector. This is called current density. And this is equal to NeVd. Your velocity is, direct velocity is a vector, current density is a vector. So the equation here, equation of magnetic force, that is equal to your NaL V direct E E V direct cross B can be changed into a new vector current density by removing this. So NeV, just replace this by a new vector current density. So force can be written as vector product of these two vectors also. Here this vector is converted into current density vector. Vector is there transferred on current density. Now another way of writing this is to change this into this is your total charge, this is your total charge, and charge per unit time. From here you can see charge per unit time is current. So in place of charge IT can be written I into T, and it is already there. direct velocity into B. But we know that your velocity into time is equal to length. So this can be replaced by length, and vector is transferred on length only. And this is a vector that has magnitude equal to length of the rod or conductor, and direction is along the current. Therefore, magnetic force on a current carrying conductor is equal to IL cross B. Take small lengths L1, L2, L3, etc. and find magnetic force due to magnetic field on these all small lengths and add. So, simple way is to write net force is summation of all the forces. And this can be integrated also for net force, magnetic force. You can integrate IL cross B.